Welcome back to the climate responsive architecture videos. So we were seeing about the microclimatic conditions. So now we have to see how the microclimatic conditions can vary according to various other external factors. So first, for example, we can consider about the wind. So if the wind direction is good, if the wind direction or the wind velocity is good, then the microclimatic variations can be better. So it can enhance the microclimate of the location. So that is one part where we can understand about the wind. So it can be of summer winds, which can give you a lot of good breeze during the daytime. So summer winds, and winter winds, of course it has to be blocked if it's a very cold wind. Otherwise you can actually if it's a normal place like in hot and dry region, even the winter winds are better. So next thing is the elevation and altitude, which also is a very important factor which can give us a better microclimatic condition. The hills and valleys, of course the climatic situation or the climatic condition will vary in hills and valleys, and the diurnal variations also will be very high. So during the daytime and during the night time there will be various air temperature fluctuations in hills and valleys. So slopes also influence the wind speeds and directions, which can indirectly and directly affect the microclimatic conditions. So if you see some of the buildings built near the valleys, so it would gain a lot of wind due to the turbulence of the valleys, or turbulence which is created by the trees, etc. So that is one advantage of valleys, and the slopes also can create a better microclimatic condition. So that is one part. And we have water, which is very important part, which can actually give us a variable microclimatic condition. So if you want to see or any location which is near the water body, so it will have a variable climatic conditions, or microclimatic conditions will vary. So if you see the concept of this during the daytime, generally what happens, anything which is near the water body, any built structure near the water body, the warm air tends to go up, and the cool air from the water body, due to the evaporation, it tries to push inside the land. So this is the natural phenomena which takes place during the daytime. And during the night time it acts little bit reverse, or it acts vice versa, where the cool air from the warm air is already risen up due to the re-radiation, and there is going to be a lot of filled up cool air here, and the cool air tries to descend back to the water body, and warm air which is already rising up, it will also have the water is going to have a little bit of higher heat latent capacity, which is going to increase the warm air more on top. So the cool air might go here to fill up the space, so that can act during your night time. So it's a very important factor whether your building or any infrastructure is located near the water body, and what type of structure is going to be there, whether it is a public space or a private space, that depends. So it is there. So it says accordingly the proximity of bodies of water body. Water moderates extreme temperature variations, raising the temperature lows in winter and lowering the highs in summer. On a large scale, it is dependable because it's a coastal region. The water body and water temperatures are dependable in a very large scale. And we have the water cycle, which is giving you the perfect microclimatic condition. For example, if you have water body, it tries to evaporate, and then, as you know, like it tries to condensate, and there is going to be a precipitation. Okay, if you have a mountainous region and also a water body, then we will consider this as an windward side and leeward side, then there is going to be a lot of precipitation, and this is called as the water cycle. So preserving water becomes a very important factor in the sustainability or sustainable future. Of course, preserving water body can give you a lot of groundwater surfaces also, and also it can also give you this climatic situation change. So water and its effect, of course, we have seen in historical evidences that most of the Mughal architecture will have a lot of water bodies and a lot of parks, a lot of open spaces, a lot of fountains were there. So all these fountains are nothing but these are the water water bodies, or the things which acts as an evaporative cooling method. Okay, so water can actually act as an evaporative cooling method, which can give you a lot of effect of moisture content around the buildings or around that location, and it can provide a better microclimatic condition. So when the water body is in shadow, for instance a pond in a courtyard, the incoming solar radiation is reduced with a further reduction in the water temperature, and also it is a water body is actually acting as an heat sink. We generally call them as heat sink. It can absorb a lot of heat, and it can retain the heat for a longer time till the night, and then it will slowly re-radiate the heat. So of course it can actually produce a better microclimatic condition. So you can see these pictures, like this sprinkling of water creates an evaporative cooling. Okay, so the method is called as the evaporative cooling, where the hot air will be here, and then when it comes through this and when it goes outside, it becomes a cool air or cool moist air. So cooling by fountains is achieved simultaneously by two different ways: by cooling directly the air of the surrounding space and also cooling the water or the pond. So these are the microclimatic inducers or microclimatic creators. Topography, as we have seen earlier, topography can give a better microclimatic situation, and according to the slopes, how you keep the building, whether you are going to keep the building on the slope, or whether you are going to try to build inside the slope, or try to come inside the slope by a cutoff method, etc. So all these things depend. Okay, and we can see this in detail also in the next forthcoming chapters. The build forms, of course, the build forms a regular build form and an irregular build form, or maybe there is a clustered build form, which can create a lot of wind deviations and also wind inductions. Okay, so the acceleration of the wind depends on the type of the build form. So if the build form is very regular, the acceleration is very slow, whereas the build form is a lot of cluster, then the acceleration is better. And the build form, again, the dependability of the vertical height. So for example, you have a very short building, and then you have a very tall building, etc. So it also depends. The wind can go up and come down like that. So the wind direction is also studied in a few case studies, which is present in the book called Sun, Wind and Light by Mark D.K. and G.Z. Brown. So you can go through that book. We have certainly the wind directions which can just go up, and it also depends. The wind forms, or the the solar cutoff. It is called as the solar cutoff. It depends on how the building is, how we have located the trees, etc. So the build forms, not only the concrete build form, of course even the natural vegetation plays a very important role in actually giving a better microclimatic conditions. Of course you can see the build form, whether you want to see it in a macro level or a micro level. In a macro level, as a build form, you can see. In a micro level, of course, you can know what type of building you are going to do, what type of openings are going to be placed in your building, whether it is going to be a parallel opening or a perpendicular opening, or even an adjacent opening, can give us the effect of the microclimatic condition even inside your building. The next thing is the build form also is considering the ground materials. So considering the ground materials, whether it is going to be grass or whether it is going to be pavers, according or dependable on the reflection, or dependable on the refraction, all the dependable of the materials, color, etc. The variation can be there in the microclimatic conditions. For example, if you have seen in a petrol bunk, there is a lot of pavers which are uncovered. So in a petrol bunk, of course, the heat reduction is very less, the heat gain is very high. So if it's a covered area of paver, the best example is our college, Karpangam Institute of Karpangam Academy, where we walk from the architecture department to the arts department. It's a covered paver area with both the sides of trees. So even if it's a paver, we have to cover it. So that also creates a microclimatic condition. So again, during the daytime, what happens? There is a lot of reflection if there is a grass or whatever it is. Again, if there is a re-radiation because of the heat, because of the pavers, and during the night it tries to radiate back. This one radiates very fast, whereas here it tries to radiate very slowly, etc. So the ground materials plays a vital role even for the microclimatic situations or microclimatic conditions. The vegetation is one of the best parts, where we have to understand what type of vegetation, or what is the type of the tree, whether it is going to be a deciduous tree or a tall tree or a short tree, or whether it is going to be a shrub, or whether the tree is going to be placed near the house or far away from the house, whether the tree is going to act as a barrier or whether it is going to act as an inducer to the wind, etc. So the tree itself acts as a shading element, and also the wind breaker, and also the wind inducer. So these trees can play a very major role in making your microclimatic conditions better to a better environment. So if you see about trees, so detailed about trees, of course we know about trees. The trees can cut off lot of solar radiations, and you can go through like how it is individually affecting, or individually it is playing a vital role in terms of evapotranspiration and etc. So if you see a clear picture of this, so it's a tree, okay. So of course if you see the solar radiation, it's almost like 734 watts per meter squared, which is the heat gain, okay. Almost it is given in somewhere in the afternoon. So if you see, if it's under the tree, okay, so the tree itself is actually almost absorbing a lot of it is trying to reduce a lot of heat, and it is giving only half of it, almost like 300 watts per meter squared. And whatever is on the ground, it tries to reflect back, and it becomes 479 watts per meter squared. Whereas if it's a plain ground, an unshaded area, it tries to re-radiate back, and it is almost like 617 watts per meter squared. So the radiation reduction is almost 50% from a tree. So we can understand how trees can be very effectively placed near your build structures, on top of your build structures, and how it can reduce the heat reduction, or how it can play as a vital role in reducing the heat, and also gaining a better microclimatic condition. So you can see some few pictures like how the trees are going to give you a lot of shades, how it is going to cut off a lot of heat, etc. And even the massing. So you can see like these buildings, you have a massing like this. So it's a cantilevered massing. The cantilevered massing also can give you a shade. So the build forms, not only the structure, even the trees, and also the massing also can create an element of the microclimatic condition. Now this is a very nice or a clear picture which can give you a perfect graphical representation of a microclimatic condition. So if you see this picture, it's a current scenario. If you see like inside your house, it's almost like 25 degrees Celsius because it's shaded inside your house. Outside your house, just imagine there are a little bit of thin trees. You've got a large paved area or a walkway without the trees, and there's a very thin tree which is going to be there. And on the road, it's going to be black color road with asbestos tar, and so it's a black colored road. So for example, even if it's 35 degrees Celsius during the daytime, your surface temperature is going to be very high in the road because of the material itself and because of the color. And here again the paver is also grey in color, and because of the material, the surface temperature is going to increase, and due to the increase of surface temperature, which is 40 degrees Celsius, the air temperature is also going to increase. So the air temperature above almost like above some 10 meters, it is only 35 degrees Celsius, whereas if you go near the road or near the pavers, it's almost like 37 degrees Celsius. So of course it's a very thin tree, and there are a little bit of shrubs which is actually having a lot of ground also. It's 39 degrees Celsius, and almost there's a major difference of about 14 degrees Celsius. Clear? So 14 degrees Celsius is very high. The difference is high. Whereas if you see another picture where there is going to be a lot of trees, and there is a lot of slope and vegetation, etc., and there's going to be a water body. So you cannot really understand, like, of course inside your house it is 25 degrees Celsius, and when you come outside the house, there are a lot of large big trees which are also called as deciduous trees maybe, and there's a very small walkway or pathway, and it is covered by two trees. So this becomes a mutual shading element for the pathway itself, and the reduction of the paver also can give you a lesser amount of heat. Okay, so again the water body, again it absorbs a lot of heat. Even though it is 35 degrees Celsius, the water body is 27 degrees Celsius, so the places near the water body is almost reduced to 1 degree Celsius. So again, if there are a lot of trees, okay, it also can give you a lot of reduction, about 2 degrees Celsius, etc. And the shaded pathway is going to give you only 28 degrees Celsius of surface temperature. The black color is called as the surface temperature, and the white color is the air temperature. So if you see, there is almost like a 7 degrees Celsius reduction. So this two pictures will clearly indicate you like how a microclimatic condition can vary because of the trees and because of the water body. So vegetation, of course, it's got its own effects, and we have certainly a small natural phenomena which takes place, which is called as evapotranspiration, which is a transpiration plus evaporation done by the trees. If you go to a dense forest, you can understand like how it's going to be very cold there. So that's the evapotranspiration. Okay, in hot and dry, just cooling the entire context there. So that is one part which the tree can do. So there is deciduous trees which can be placed on south and western sides if you are in the northern hemisphere. Okay, and it depends again if you are planning accordingly to the northern hemisphere or the southern hemisphere. The placement of the trees depends on the design decision by the designer, that we can see in unit number 5 or 6. So the trees grouped together can actually create a lot of cooling which can be done. It says it is generally agreed that there is an air temperature difference of about 2 to 3 to 6 degrees Celsius between the inside of a larger green area and the surrounding built space. So the best example if you see is like Chandigarh, of course the planned city, and a few more cities like Bangalore where they have not cut down a lot of trees. So because of the trees, the climate is always having a good ambient temperature which is very suitable for us to live there. Yeah. So the trees can act as both the sound buffer zone, and also it can also give us a microclimatic enhancing situation. So we try to have a very small space in the urban setup. So what we do is the next option is to go for a roof garden. The roof gardens, of course, the concept is actually slowly improving. You can actually learn about these roof gardens in the next forthcoming chapters also. So one of the few things which you can do, even if you are in an urban setup, you can actually go for a roof garden. It's very easy. So of course you have a terrace with you, so the whole terrace can be utilized for a roof garden. If you build a house of about 1000 to 1200 square feet, okay, of course the built up area can be more, but the roof area, you will actually get the whole plinth area as the roof area, rather than just keeping it idle. You can use it for the roof gardens. So of course there are a few good ideas of the roof garden where you can see a few people are going for the roof gardens. So roof garden is one of the best element or best ideas for forthcoming future. So next thing is, in microclimatic condition we have something called as an urban heat island profile. So this urban heat island profile is a very new or a technical term where it says we have an higher summer temperatures. When you have a summer temperature in an urban setup, the summer temperatures are very high. It tries to create a lot of heat near the urban areas or in the downtown areas, which is actually created because of the elements which are used there or because of the built forms itself. Clear? So what happens is, if you see the next picture, you can get a clear graph of it. So you see a downtown. A downtown is like a town or an urban or CBD area, central business development area, where you have lot of buildings. Okay, you have a lot of commercial buildings, etc. You have a lot of bigger roads or a larger, wider roads, etc., and less number of trees, and you have got pavers also, etc., and so on. So of course in a master plan they should have planned in such a manner that it has to accommodate a lot of people, etc. But the problem is, when you do without the trees and without proper planning, the downtown area will have a increase in air temperature first of all, because of the increase in the surface temperature, and that is because of the material usage. So when you have used when you have used a lot of concrete, when you have used a lot of glass facades, when you have used a lot of other pavers, etc., that itself is going to increase your surface temperature. So due to which the air temperature is also going to increase. So the graph is clearly showing you, like this dotted line is the air temperature, if you can see. Okay, so during the day, whatever it is, and this dotted line in blue is the temperature, air temperature, which is during your night time. So if you see the graph, the surface temperature during the daytime is extremely high in your downtown areas. It's extremely high in your downtown areas. So for example, if you are in Coimbatore, so downtown area is somewhere like your Avinashi Road. Okay, so maybe like your Avinashi Road, it's got a wider road and it's also like a downtown area. And maybe like even your Okadam area, so that is also a downtown area where you've got a lot of commercial spaces in like an NSR road or whatever it is. So those areas will be a little bit hotter. Of course your crosscut road, it's a wide road with a lot of commercial spaces. Of course to a few parts there are no trees at all. Okay, so those downtown areas will have a lot of surface temperature increase during the day. So next thing is, in an urban residential area, of course there will be a little bit of increase. So you can see a surface temperature increase, air temperature to surface temperature is also very high. And if you have a warehouse, like if in Coimbatore, if you have Sitcos or some other warehouses where you're going to have some automobile industry or some other cement industry, or maybe your granite industry, etc., or maybe your mechanical industries. So this warehouse will create a lot of heat, because the warehouse itself is going to create a lot of heat. And moreover, the structure, the roof structure is going to be something like galvalume or something like asbestos, etc. So they also is good. That roof structure is also going to create a lot of heat radiations, etc. So that is going to give you a higher amount of surface temperature. And there is a cluster of warehouses. That cluster is also going to give you a lot of transportation there. So the lorries can move around in there. So that will actually create a lot of urban heat island. Okay, so that is going to be there during a summers. And very interestingly, if you see a pond, so this pond is going to reduce your urban temperature less than your air temperature itself. Your surface temperature is also going to reduce less than your air temperature during the day. And suburbans, it is little higher, but whereas in rural areas it's very low, because rural areas are widespread first of all, and it has got a lot of agricultural spaces, and lot of water is also used for the agriculture. So that's why the daytime temperature of the surface temperature is a little lesser in the rural areas. And of course, when you go this side, you see a park. So the park is also reducing a lot of surface temperature, because it is well shaded first of all, and it's got a lot of vegetation which can create an evapotranspiration. So that is one part where the park is also a major factor or a contributing factor. For example, our VOC park in Coimbatore. So it's a major factor or a contributing factor which can reduce the microclimatic conditions. Of course, your race course is there. It's also reducing the microclimatic conditions there at that race course, because of the wide range of trees which are present there. Again, in suburban and rural, it is lesser. And if you see in the night time, there is a little bit of variation in the pond, because the water body, as we dealt earlier, it will slowly radiate the heat above on top. If you see the downtown, the air temperature and the surface temperature is almost the same, which is not even reducing, because the heat which is already built up here is not trying to go out because of the slow heat transfer from inside the building to the outside of the building, inside of the building to the outside of the building. So that's why the air temperature is almost the same. Whereas the surface temperature will suddenly reduce here in a warehouse, because sometimes what happens in a warehouse, it's a very thin material. So the thin material, it can re-radiate faster. Okay, so that is why it is actually producing or making the surface temperature little lesser after your work hours. Like after the work is completed by 5 o'clock or 6 o'clock, and it's left very idle and nobody is there in warehouses or industrial areas, and suddenly it reduces the surface temperature, because the material is very thin. Okay, and even in rural areas, the material which is used is not concrete or brick walls, whereas they have used something like a thatched roof or something like an earth wall, etc. So that also can reduce the earth surface temperature lesser. So this is a very interesting chart where you have to intricately see how an urban setup is there, and how the urban setup is actually giving us the microclimatic condition. Okay, so like what to do in the future, okay, because of this microclimatic, how to gain your microclimatic condition by your way of design. So of course there are few things which you can learn from Climate Responsive Architecture book by Arvind Krishnan. So these are some of the calculations of latent heat transfer and advanced energy, etc., for the microclimatic situation and heat island effect. So generally, if you see, it's a vast area with lot of apartments. Okay, so you gain lot of heat because of the apartments. Lot of heat gain is due to the buildings, etc. So there are a lot of thermal properties which is actually contributing to the heat island effect. Okay, there is a lot of urban greenhouse gases. So all these things are very important. So generally, we need to know how these things can be replaced, or how a designer can think about giving a better microclimatic condition by reducing the pavers and giving them full of natural environment, and giving them large water bodies, etc., preserving the water bodies. Now Coimbatore, as a smart city proposal, it is trying to preserve the water body. where as a very futuristic thinking architects, you must also start architects and designers, you must also start thinking how you can preserve water bodies, how you can make a better environment. So the next chapter is going to be thermal comfort. We will see in part number 4 for the part number 5 for the next chapter, thermal comfort. We'll continue in part number 5. Thank you.